Hello everyone, I am Abhilash and I am here with Lakshmi. We are currently pursuing MCA in Chanakya University. Today, I am excited to present our research paper titled Regression Machine Learning Models for Short-Time Prediction of Genetic Algorithms Result in Vehicle Routing Problems. This work bridges two powerful fields, operations, research and machine learning to solve a critical challenges in logistics, optimizing delivery routes faster than ever before. Under the guidance of Professor J.B. Simha, we developed a framework that cuts computation by 1800 times using AI predictions. Today, I will walk you through our methodology, key results, and why this matters for real world applications. So, let's dive in. Introduction. The study bridges two powerful optimization domains. They are genetic algorithm. Next one is machine learning. Now let's see the genetic algorithm. A materialistic inspired by a natural selection that evolves solution to optimize problems over generations. The another one is machine learning, especially regression models used to predict outcome based on the data patterns. Now let's see the problem. Uh, Basically, the vehicle routing problem, the VRP, given a depot and a set of customers with the demands to find the optimal routes for vehicles to minimize and distance for our time, subject to vehicle capacity constraints. Okay, now genetic algorithm are good at solving vehicle routing problem, but take a time to converge. To overcome this idea, predict the final result early in the genetic algorithm execution using machine learning, thus saving lot of time. Now let's see the real-time example. Like a GPS that learns from the past traffic data to predict the fastest route after just a few minutes of analysis. Now let's see why this research matters. Real-time decision making in logistics, example routing, uh, it needs real-time logistics to take decisions, need speed, example same day deliveries in a metro cities. Full genetic algorithm takes hours, but machine learning predicts in lesser than 1 second after 5% of genetic algorithm progress. Now let's see the explanation. The machine learning reduces computational time from overnight on a real time. Now let's go through the real time example. A food delivery app rerouting deliveries instantly when a new order pops up. That's it, a basic and simple real time example. The OpReMaL framework. What is OpReMaL framework? Now let's see. The expansion of OpReMaL is operations research problem solving using machine learning. In this framework, it has two main steps. The step one is data generation using operations research to solve VRP instance using GA, and it basically solve the VRP or vehicle routing problem instances, record features like customer locations, demands, etc. And second one is machine learning prediction. It train models on early genetic algorithm results in the 5% of progress to avoid running full GA by learning from the partial data. Like a chef tasting a soup early to predict a final flavor without waiting hours. Okay, now let's go through the case study. Vehicle routing problem solving by GA. We already know GA's genetic algorithm. So The genetic algorithm setup chromosomes equals to roots crossover mutation to evolve solutions. VRP parameters 700 customers, 4,550 instances. Truck capacity constraints like simulate real world logistics scenarios. We can just imagine a warehouse serving 700 stores optimizing 50 trucks routes every day daily. Input and output data of machine learning models. Now let's see inputs: customer distance, demands, demand states, vehicles capacity, etc. The output: total route distance, GS final result. I already here represented the overview how input and output data of machine learning models works. And machine learning uses the features of predict to the optimal route distance. For example, a customer A has a 5 miles from the depot. He needs 50 units of product. The outcome of output is total distance equal to 200 miles. Okay, next now let's see machine learning models tested. Linear models and Bayesian, distribution based, robust regressors, ensemble. Now let's go through the linear, RidgeCV, Bayesian, and ensemble, and random forest also. The random forest performed the best compared to the models of accuracy or speed. Random forest on this task. Like it testing sports cars, random forest versus sports car versus sedan. Like random forest is like a sports car and sedan is linear regression. For a race, random forest was the fastest car and it won the race also. Performance evaluation. The performance evaluation and the speed comparison. I added one like type of data. Random forest had lowest error MAE 3439. MSE or RMSE are similarly strong. Now in next slide we can see what is MAE, MSE and RMSE. It proves random forest reliability for VRP predictions. For example, predicting a 1 lakh mile route within plus or minus 3,493 miles to accurate enough for logistics planning. Let's go through this image. The performance evaluation of the three types, basically metrics used and best performance and speed comparison. In speed comparison, the genetic algorithm and machine learning are used. In genetic algorithm, it takes 1800 seconds and machine learning predictions is lesser than 1 second. Machine learning up to 1800x faster. And best performers are random forest, we already know, and Poisson regression and RidgeCV. This is the performance MAE. The MAE full form is model performance based on mean absolute error. It is to evaluate how each regression model predicts the final objective values of genetic algorithm using MAE metric. Okay, this is the MAC model performed based on the mean squared error MAC To access the prediction accuracy of each regression model using MAC, a metric that penalizes larger errors more heavily than MAE. Random forest again achieves the lowest MAC, uh, reinforcing its consistency to minimizing error. Models like Elastic NetCV and Gamma Regressor show much higher MAC, but it's indicating instably or poor generalization. Random forest maintains top performance even under the MAC, proving a robusting in handling outliners and high variance predictions in the VRP and GA scenario. Model performance based on RMSE. It means root mean squared error. To compare models based on root mean squared error, which reflects both variance and bias and maintains the same unit as the target, like objective, the best objective value. Random forest again leads with the lowest RMSE. I already uh, shown plus or minus 3493, indicating excellent overall predictive performance. The random forest consistently outperforms all the models across MAE, MAC, and RMSE, confirming it as the most accurate and reliable model for predicting GA performance in the VRP. Now, let's see key improvements are over the original regression framework. We already see the previous slides, what they are implemented, and now we are going through what are the improvements we did in this research paper. Visualize the pairwise correlation between all numerical features and target variable best objective value. Basically, it has the feature correlation heat map. Okay. It basically number of customers, average demand. It calculate this both and gives the total distance. More customers is basically more customers is equal to higher demand in longer routes. In the right side, we can see a heat map showing a rush hour delivery strongly impact total distance. This graph shows that the top two features versus target. Basically, new customers and average distance depot predictive, linear relationship justify regression models. The graph showing more customers is equal to larger routes as a straight upward line. In this graph, we can see future importance in random forest. Number of customers, average distance depot, vehicle capacity. Focusing on these improvements predictions, for like example, uh, prioritizing traffic, distance, and truck size for route planning. Now let's go through graph 4. Residual distribution error histogram. Basically, error centered around 0 is equal to unbiased predictions. No systematic over under prediction. Histogram shows most errors near 0, like as a well and calibrated speedometer. We can see here in the graph. Basically, it shows the distributions of a residuals The graph 5 pair plot of selected features. Explore derivative relations between key features like target and grid of scatter plots. Visual pattern recognition across multiple dimensions. It detects the multi-consistency over clusters and may affect model training. A pairwise relationships between selected features and the target reveal consistent trends. There are no extreme outliers or highly non-linear interactions supporting effective model training. We implemented graph 6, actual versus predicted, sorted line plot. It validates the model accuracy across all scenarios. Graph showing predicted and actual routes overlapping like a parallel train tracks. Now let's see learning curve. It's basically MAE decreases with the more data, no overlifting. This model improves with more examples, like a student scoring better than more practices, more practice test. As a how prediction error evolves as more training data is used. This is the cumulative feature importance graph. Here, it shows how many features are needed to explain a certain percentage of the model's predictive power. Rapid increases to 95% importance with few features indicates a strong core subset. The red threshold line allow quick future selection decisions. The top 4 and 5 features account for over 95% of the model's predictive power, and this suggests is the possibility of reducing input dimensionality with a little to no loss in accuracy, improving efficiency. Unveiling power of machine learning using decision making. This is the insight. It skips genetic algorithm runs. Trust machine learning. It basically trust machine learning predictions. Retain machine learning when conditions change. Example, new customer locations. It enables the agile decision making. A logistic manager updating routes daily without waiting for a genetic algorithm results. How this works. Now let's see the conclusion. Random forest is a fastest and accurate 1800 times its speeds of works for a large scale VRP. For example, in future drone delivers using system to reroute mid-flight. The regression machine learning models can accurately predict a genetic algorithm outcomes the vehicle routing problem. This approach supports real-time scalable optimization in logistic and smart transportation. A small number of features like new customers, average distance, and distance depot provide the most of the predictive power. The OpReMaL framework enables fast, accurate predictions without full genetic algorithm runs. Basically, the random forest showed the best performance across all matrices like MAE, MAC, and RMSE. Now that we have covered the theoretical framework and results, I will hand over to my friend Lakshmi, who will take you through the implementation details. Lakshmi will demonstrate how we translated these concepts into the code, including key challenges and solutions. Over to you, Lakshmi.
Hello everyone, I am Lakshmi. I am going to explain about this code. First, we need to install required libraries, and next we need to import libraries like pandas, numpy, matplotlib, sklearn, and we need to upload the dataset using this command df pd dot CSV. There are two part in this X and Y. X train are used to train the data, train the models, and Y test is used to test the models. Define all models. In this step, it will define all 17 models like random forest regression, linear regression, etc. And the fourth step is train and evaluate. In this step, it is used to train the models and evaluate the models. There are three types of methods. First one is MAE, second one is MSE, and RMSE. These methods are used to test and train the models. And next there are GA setup and instant configuration. There are four set of instance. It is used to create a table showing four set of VRP instance, including data, including details like number of customers, populations and population size, and computational time. It is used to describe how the data set was generated and the generic algorithm. It helps to interpret different performance across instant of sizes, and it has the average time, and it is smallest time is 4 and largest time is 1811. And next table is GA parameters and problem solving. It is used to list the parameters using the GA, selection, crossover, maturations, etc. And it defines the fitness function as minimize total distance. And it is used and it provides the reproducibility of the problem solving method. And it consists characters of parameters and values. Regression model description. In this step, it describes all the models of all models, 17 models, and it explains the description of this model. There are 17 models in this code. It explains the description of this. It explains the description of this models. And next fifth step is create data frames. It is used to create a data frames. It is used to create a data frames using three matrix MAE, MSE, RMSE. It is used to create for all the 17 models, and in table 5 MAE for individual sets. This command is used to create for individual model. It has four set of instance, and it shows the best MAE, and it represents and it calculate the best models, and it calculates the percentage error and computational time. And next one is MAE plot. And this is a graphical representation of MAE. This represents the this represents how graph how and this is a graphic. This is a bar graph. This represents how the plot this this represents how the performance of MAE. And next one is MSC. This is the performance of MAE. This is a particular performance of MSC. And next one is RMSC. This is the graphical representation, and this is the performance of graphical representation. This is a particular performance of this instance. And next one is future correlation heat map. This it is used to calculate the strongly each features in related to others. The heat map is helps to identify which features are mostly correlated with the target, and the top correlated features, or this is a correlated graphical representations, and it has three types: minus 1 point, it has minus symbol like minus 0.19. It represent a negative numbers, and it has 1.00, it represent a positive numbers. Like 0.0, it has null values. And next is scattered plot of top two correlation futures versus target. There are two graphs, there are two graphs of top two features versus target. This represents the plots of relationship between the targets, helps to visualize where a linear or non-linear pattern exists. And the next one is feature importance using random forest. It is used to train the random forest models, and measures the importance of each features in making a prediction. This is this is a graphical representation of future importance. This is a plot of a this is a plot of a bar chart of future importance. And next one is the error distribution graph. This shows how errors or variations from one point to another point, and it shows how distribution of prediction errors. This represents the distribution prediction errors, and in a center bell-shaped plot suggests the model in unbased. And next one is a pair plot of selection futures. This is a representation of pair plots of selection futures. It has many graph in this. It has many graph in this one image, one graphical representations. And another one is next graph is actual versus predicted. This graph represents the compares actual versus predicted value in sorted order, and it helps to visualize the value of access how well the model tracks the true values, and it starts from zero and ends to the 3 lakh. And next is graph 7, learning curve. In this graph has two line points. It has green color line. It represents the train MAE, and red color represents the test MAE. Green and red line represents the train and test the models. Test how the model performs changes with increasing training data size, and decreases the curve. The flattened suggests the model has learned enough and added more data. And next one is cumulative feature important. Cumulative feature important. This represents rank features by importance and shows how many features account for most of the predictive power. And it is useful for the and it is useful for identify the minimum number of features needed for good accuracy. And this is the last graph of this code, cumulative future importance. Thank you.